In a previous lecture, we have discussed about a registers and a SIP registers. Registers are used for as a memory element, and the SIP registers are used for the movement of the data. Means you can shift the data from left to right or right to left, and you can have a number of operations in a SIP register. We have seen that there are four different modes of the SIP register. That the first mode of the SIP register, that is known as a SISO. SISO means it is called a serial input, serial in, serial out. In SISO, the data will be entered in a serial fashion and it will also come out as a serial. Then the second one is a SIPO, which is known as a serial in, parallel out, where the data will enter in a serial fashion, but you can obtain the data parallel in the output of the SIP register. Third one is known as PISO, that is the parallel in, serial out. And the fourth SIP register is a PIPO, where the data are also entered parallelly, as well as you will also get the data parallelly at the output. So in this way we have four different mode of the SIP register. In this video lecture we will discuss the serial in, serial out SIP register, as well as we will also discuss the serial in, parallel out SIP register. Now let us see what is the SISO. Basically in a SISO, here we know that. So we know that the register is nothing but it is a group of the flip-flop. Here in this diagram we have four different flip-flops. This flip-flop is A flip-flop, B flip-flop, C flip-flop and D flip-flop. We have four flip-flop, means it is a 4-bit register. Here at the input we apply the data in the serial form, and you will get the data in the output as a serial form. Basically here also we apply the clock. This clock is applied parallel to all the flip-flop. So all the flip-flop will be triggered simultaneously. Now suppose when we apply the 4-bit number, binary number at the input of the SIP register, then first of all whatever the LSB is there, this is the LSB of your binary number and this one is the MSB of the binary number. Now with the first clock pulse, this LSB will be entered into a flip-flop D. Then with the second clock pulse, this one will be transferred to a flip-flop C. When we apply the third clock pulse, it will be transferred to flip-flop B, and then finally with the fourth clock pulse, it will be appear at the output. So here in the output, we are taking the output from the flip-flop A. So after the fourth clock pulse, this one is going to be appear at this output. So in this way, this data is moving from a left to right. So this is known as a right shift register. This is called a right shift register. Same way, you can also have a left shift register. So one by one, each bit of your input data will be entered into the register and it will move in a serial fashion and you will get in the output. Now let us see what is the logic diagram of a SISO. So here you can see, here we have a logic diagram where the four flip-flops are there. This is the flip-flop A, flip-flop B, flip-flop C and the flip-flop D. All these flip-flops are connected in series. It means the output of the flip-flop D is connected to input of the flip-flop C, output of the flip-flop C is connected to input of the flip-flop B, and the output of the flip-flop B is connected to input of the flip-flop flip-flop A. And the output of the flip-flop A, this is my a serial out, and my serial input data is given to a D flip-flop. Now here you can see this all the flip-flops are a JK flip-flop. Now instead of the JK flip-flop, you can also use a D flip-flop. The working of the circuit will remain as it is. Basically here if you see in the D flip-flop, between the J and K, we have connected a NOT gate. So this connection is indicate that this flip-flop is working as a D flip-flop. It is working as a D flip-flop that already we have discussed in a flip-flop conversion circuit. Then second thing, here we have applied a clock parallel to each flip-flop that you can see. The same clock is applied, and it is these flip-flops are operating on a negative edge because here we have a circle at the input. So this is going to operate at a negative edge of the clock pulses. Then if we see in a diagram, then this plus VCC is applied to all the flip-flop, and this terminal is nothing but it is called a preset. This is for presetting means when we apply then this preset are a active low. Here you can see it is a active low. So when this terminal, this VCC, instead of VCC, if this is connected to ground, then all the flip-flop is going to be in a set condition. In set condition means output you will get a 1 1 1. Here this output of the flip-flop will be a high, so that is known as a set condition. Then here if we see, then this is the clear input of all the flip-flop. These clear inputs are also connected to a VCC. Now this here, the clear inputs are active low. They are active low. So when we are connecting this terminal to the ground, instead of VCC, if this is connected to ground, then the flip-flop is going to be reset. Here it is going to be reset like this. So in this way, the flip-flop have the preset and the reset facility. These are the asynchronous input. Asynchronous input means without clock pulse, directly you can set or reset the flip-flop, or in other words we can say that directly we can clear the register by by connecting this clear input to the ground terminal. Now let us see the operation. For the operation, first of all we have to clear out all the SIP registers, remember, because whenever we switch on the circuit, then the output of the flip-flop will be undetermined. We do not know the output of this flip-flop is going to be high or low. So before you enter any data, we have to reset the flip-flop, and for resetting the flip-flop or for the clearing the SIP register, first of all we have to connect this terminal to the ground. So the clear input will be a active low. So due to this, here all the flip-flop output is going to be a 0. So we are not applying any clock at this moment, but we are clearing the SIP register, means whatever the previous data is there, it will be cleared out. After clearing the SIP register, you have to remove this ground and apply the VCC. So when this preset input and the clear inputs are high, then we have a normal operation of the SIP register. We have normal operation of the flip-flop, correct? Now let us apply a 4-bit. Here we have a 4 flip-flop, so it is a 4-bit SIP register, and therefore it can store the 4-bit data. So suppose my data is, my binary number is 0, 1, 1, 1. Correct? This is my LSB of the data and this is the MSB of this data. Now simultaneously also we will prepare a truth table for the SIP register. So initially when we are not applying any clock, at that time here my LSB is going to be appear at the input of the D flip-flop. Correct? So 1 is going to be present here. 1 is present here means we can say my input is X. At that time all the flip-flops are in a reset condition. So they are 0, 0, 0, 0, 0, 0. Now we applied a clock. So here these flip-flops are operating with the negative V. So here the clock is applied, first clock pulse is applied with the negative V. So here I will write the negative V and this is the clock number 1 is there. You can see clock number 1 is there. When we apply this negative V, then whatever the 1 is at the input of the first flip-flop, that is a D flip-flop, it will be transferred to the output of this flip-flop and this become a D. Now at that time the input of the C flip-flop was 0. So now it will be transferred here and this become a 0. Here the input of the A flip-flop is also a 0. Here, sorry, the flip-flop input of the B flip-flop is also a 0. So this is going to be a 0 here. Input of the A flip-flop is 0. So this will be also a 0. So after applying the first clock pulse, what will happen? That this input is transferred to a D flip-flop become a high and these are remaining 0. Here this 0 is transferred to C flip-flop, this 0 is transferred to B and this is transferred to A flip-flop. Now when this first clock pulse is applied, correct? Then the second bit we applied at the input of this flip-flop and that is another 1 is present. So my input is a high level. Now we applied a second clock pulse. So with the negative edge of this second clock pulse, whatever the 1 is appeared here at the input of the D flip-flop, it will be transferred to the output. This output become a high. Then at that time the input to the C flip-flop is 1 and it is going to be transferred in the output of the C flip-flop become a 1. Here input to this B flip-flop is 0 and it is going to be transferred here. Input to the A flip-flop is also 0. So here it is going to be transferred. So when we apply the second negative edge of the clock pulse, then this one, here this one is transferred to D flip-flop, this one transferred to a C flip-flop, this 0 is transferred to a B flip-flop and this 0 is transferred to a flip-flop. Now at this point my third bit is going to be appear here, that is also a high level. So here we write the input is 1. Now when the third clock pulse we applied, that is a negative edge of the third clock pulse will be there, then this one is going to be transferred. This one of QD will be transferred to QC. This one of the QC will be transferred to QB with this negative edge and this 0 will be transferred to AQA. So here this one is in the output of the D flip-flop, this one is in the output of the C flip-flop this one is in the output of the B flip-flop, and the 0 will be at the output of a flip-flop. Correct? And now my fourth input is 0, that is going to be appear here. So my input is 0 when we apply a fourth clock pulse. Then the same way here the 0 will be transferred to the D flip-flop, the 1 will be transferred to a C flip-flop, this will be transferred to a B flip-flop, and this one is transferring to this A flip-flop. So my data input, remember, my data inputs are 0, 1, 1, 1, and after the clock pulse, fourth clock pulse, here also you can see that 0, 1, 1, 1 is in a shift register. So after the clock pulse, fourth clock pulse, all the data are stored by this A shift register. Now when we applied, remember, when we applied a fifth clock pulse, then this one will be appear in the output. With the sixth clock pulse, this one is going to be appear in this output, and when the seventh clock pulse will be there, then this 0 will be appear in this output. So here if we see the serial out, then this first one will be present, then the second one will be in the output. Here the third one will be there, and then the 0 will be in the output. So in this way, this data is moving serially in the SIP register, and it is also come out serially in the output of the SIP register. Here you should remember that if we have the 4-bit data, then we require the 4 clock cycle to enter this binary number. If we have a 7-bit data, then we require the 7 flip-flop, and the 7 clock pulses are required to store this data. But if you want the output serially, then some more clock pulses are required. Here you can see the 5th, 6th and 7th pulse are there. So here you can say the n number of the clock pulse will store the data, and n minus 1 number of the clock pulse is required to get the output, to get this output. So the total you require 2n minus 1 clock pulses, 2n minus 1 clock pulses are required to get the output in the serial fashion. So here the data are moving from a left to right. They are moving from left to right. So it is a right shift register. Now the same logic also you can apply for the left to shift register. In that case, this QA will be connected to here, and then the QC will be connected here. So that you can think about how we can move the data from left to right. Now let us see the waveform at the output of the each flip-flop. So here my inputs are these are the clock pulses, correct? And we have 4 different flip-flops. So we draw this waveform for a QD, QD, QC, QB, and QA. Correct? Here this flip-flop are operating at a negative edge. So my first negative edge is this, second negative edge is this, third negative edge is this, and this is the fourth. So this is the first negative edge, second negative edge, third negative edge, and the fourth negative edge. So at 4 different negative edges, let us see what is the output of the each flip-flop. Now you can see after the first negative edge, the QD become a high, and QC, QB, QA are 0. So initially all the flip-flops, remember, initially all the flip-flops are reset. So we can draw in this manner This is a zero condition. This is for the flip-flop C. This is for the flip-flop B. And this is for the flip-flop A. So these are 0, 0, 0, 0, 0, 0 and 0. So after the first clock pulse, the QD is high, that you can see. The QD is high. QB, QC, QC, QB and QA are 0. So we can draw it here. The QD is high till the second negative edge is coming. QC, QB and QA are 0. When the second negative edge is coming, then the QD is high, QC is high, QB and QA both are 0. So here if you see, the QD is high, QC become a high, QB and the QA are 0. Then with the third negative edge, QD, QC and QB all are high and the QA is 0. So here high, this is also high and QC become high. So we have this output. And with the fourth clock pulse, QD becomes 0 and B, C, B and A all are high. Correct? So if we see this waveform, with the fourth clock pulse, QD become a 0. Then this is remaining high. This is also remaining high. And here, whatever the fourth clock pulse is there, this become also high. So now, if you see that output QD, QA 0, 1, 1 and 1. So if we see at different stage what is the content of a register, then here you can see that when we have no clock pulse, then the content of the register is 0, 0, 0. Then we have this 1, 0, 0, 0. So this content is 1, 0, 0. With the second negative edge, here it is 1, 1, 0, 0. So this is 1, 1, 0, 0. Then the third 1, 1, 1, 0 is there. 1, 1, 1, 0. And with the fourth negative edge, we have a 0, 1, 1, 1. So in this way, my input is 0, 1, 1, 1. Then after the fourth clock pulse, the SIP register contains a 0, 1, 1. So this is, and then when we apply a fifth clock pulse, sixth clock pulse, then this one is going to be transferred serially in the output and it is going to be appear at yi. So in this way, the data is entered serially into the SIP register as well as you are also getting a serially in the output of the SIP register. The only thing is that here you require, and that is you can say kind of a disadvantage, that you require the n number of the clock pulse to enter the data and another n minus 1 number of the clock pulse required to get the output. Total 2n minus 1 clock pulse are required for shifting the data from left to right. Now, what is the use of this SISO SIP register? So basically, it is used in a communication. In communication means when you want to transfer the data from one place to another place, then here whatever your parallel data is there, it has to be converted into a serial form. So suppose we have one of the computer here and another computer is here. Now you want to transfer the data. Here my data is A0111. So basically we have the 4-bit data. So what we require, that the 4 different lines were required for transferring the data. So here the parallelly this data will be transferred from one computer to another computer. But if we have SISO system, then only one connection or the only one wire is required to transfer the data. So here what will happen, suppose the distance between the two computers is large, like suppose it is a 1 kilometer, then here you require a cable of a 1 kilometer. But in this case you require a length of the cable of a 4 kilometer because the 4 wires are there. So you require the 4 kilometer long copper wire, and we know that the copper wire are very costly. So when you transfer the data parallelly, then it is a costlier. But if we transfer the data serially, then here we require only one wire. So first of all, this LSB will be transferred, then the second bit will be transferred, third bit will be transferred, fourth bit will be transferred, and it will be reached to another computer. Now in another computer, that whatever the data is coming serially, it will be converted into a parallelly for the further processing. But the transferring of the data will be easy if we have a movement of the data in the serial fashion, and therefore the serial in serial out SIP register are used for transferring the data at a long distance. Okay, now we will see another type of a SIP register, that is the serial in parallel out. In serial in parallel out, again we have this kind of the connection of the flip-flops, where we have a flip-flop, B flip-flop, C flip-flop, D flip-flop. They are connected in a series. The logic diagram for the SISO and the SIPO both are identical. Only thing is that we observe the data in a parallel form. So when we apply any data at the input, like a 1011, then we know that with the first clock pulse, this one is going to be appear here. So this output will be a 1, here all this output will be a 0. Now when the second clock pulse is applied, then this one will be transferred to this, and the second one is going to be appear here. So 1 will be there, 1, and here we have a 0, 0. When the third clock pulse will be there, the third bit will be appear here, and this one is shifted in a right side. Then when we apply the fourth clock pulse, then the MSB will be transferred to a QD, and we have a output. So here we see this data in parallel form. So the output of the flip-flop D is connected to flip-flop C, C is connected to B. But we are not taking the output from the QA. If you take the output from QA, then it is a serial fashion. But we are taking the output from the QD also, QC, as well as the QB and the QA. So this is called a serial in parallel out SIP register. Now let us see the logic diagram. This logic diagram is identical to a SISO. So now look at this logic diagram of a serial in parallel out SIP register. We have 4 different flip-flop A, B, C, D are there, and there is a common clock applied to each flip-flop, and they are a negative age trigger flip-flop. here we have used a D flip-flop directly. Now you can also use the JK flip-flop. Here the output of this output of the D flip-flop is connected to input of the C flip-flop. Output of the C flip-flop connected to B, as well as the output of the B is connected to A. The only thing is that here, if you see the logic diagram of the SISO and the SIPO, in the SISO we apply the serial input will be there, and the serial output was present here. Now instead of that, here whatever the output of the each flip-flop is there, these are representing the output of the SIP register. So the QD output is there, QC output is there, QB and the QA. So we have 4-bit binary number. So we have 4 different outputs of the flip-flops are there. So QD, QC, QB, QA is representing the output of a SIP register, and we observe this data in a parallel fashion. So this is a serial in parallel out SIP register. Then every flip-flop has a preset facility. So this VCC is used for the presetting the flip-flop. Means when we apply the this is the active load that you can see. So when this is connected to ground, then all the flip-flop is going to be set. And here we have clear facility, and it is also a active low. So when this terminal is connected to ground, then all the flip-flop is going to be a preset. So before you enter your data, you have to clear the SIP register. So, and for that, here this terminal will be connected to ground. And when this is connected to ground, then this output of this flip-flop become a 0, this will be 0, this will be 0, and this will be, you can say the QD output is 0, QC is 0, QB is 0, and the QA is 0, means my flip-flop is clear out. Here when you clear this, at that time you don't require any kind of a clock pulse. It is a asynchronous input is there. Now let us apply some data at the input. Now when we apply the data, then we have to remove this ground. Then the flip-flop will remain operative, otherwise it will remain in a reset condition. Now my input data is, let us say, 1011. Correct? So after applying each clock pulse, what is the position of the 4 flip-flop? Let us make a truth table for that. Here we will write the clock pulse. My data input is there. Then what is the output? QD, QC, QB, and QA. Or we don't draw a line. Okay. So here I will write a clock pulse. My data input. What is the QD, QC, QB, and QA. So initially we are clearing this flip-flop. So these are 0, 0, 0. We don't apply the clock, but at that time my LSB of this data is appeared here. So data input is 1. Correct? Now when we apply the negative edge of this clock pulse. So first negative edge of the clock pulse number 1, we apply this negative edge. So what will happen? That this 1 will be transferred here. This 0 will be transferred. This 0 will be transferred here, and this 0 will be transferred to QA. So after the first clock pulse, if we see my QD is 1, this is 0, 0 and 0. So here with this first negative is QD is 1, then the rest of the three inputs are 0. But meanwhile, the second input is also present, second bit is also present at the input of the D flip-flop. Now, when this second negative edge is coming, then this one, remember, this one is going to be appear at the output of the D flip-flop, and this one is appear at the output of the C flip-flop. This 0 will be transferred here, and this 0 will be transferred here. So after the end of the second negative edge, this 1 is transferred to QD, this high level is transferred to QC, and this is transferred to QB and QA. And meanwhile, my third input is present at the input of the SIP register. Correct? So after the second clock pulse, here what are the output QD, QC, QB, QA? This is a 1, 1, 0, 0. Remember. Now, when we applied a third clock pulse, negative edge, then the third bit is transferred to AQD, that is my 0. Here, this 1 is going to be transferred here. This 0 is transferred to a QB, and this 0 is transferred to QA. So here if we see, this 0 is transferred like this, 1 is transferred here, this 1 is transferred to QB, and this 0 is transferred to QA. So here if we see, the output of this flip-flop, after the third clock pulse, the QD is 0, QC is 1, QB is 0. Here we have made a mistake that I am correcting. Here actually this is not a 0, but it is a 1. So this one is going to be transferred. So this is 1 and this is going to be 0. When the fourth negative edge is coming, here my fourth bit is the 1. So this one will be appear here. This 0 will be appear at QC. This one will be appear to a QB, and this one will be appear to a QA. So here if you see in the truth table, then the MSB, that is the last bit of your data, is now transferred to QD, that is a 1, and this 0 transferred to QC. This QC is transferred to QB 1, and the QA is going to be 1. So if you see what are the output, then this output after the fourth clock pulse, if you see this output, here the QD become a 1, QC is 0, QB is 1, and the QA is also 1. So what is my input binary number? The input binary number is 1011, and after the fourth clock pulse, what is the QA, QB, QC? That is also a 1011. So that my input is 1011, and that is equal to here the QD, QC, QB, QA, and it become a 1011. Here, what is the advantage? Advantage is that to enter the 4-bit data, we require a 4 clock pulses. So if we have the n-bit data, then you require the n clock pulses, and at the end of the fourth clock pulse, you have this output. Whatever your data is there, it is appear at the output of the fourth clock pulse parallelly. In a serial output, you require some more clock pulses to get the output. So this is known as, here the data is going to be entered in a serial fashion and we get the output in the parallel fashion. This is about the serial in, parallel out SIP register. In the next video lecture, we will discuss another mode of a SIP register, that is the parallel in, parallel out and parallel in, serial out SIP register.